Right, we're back looking at the 64K RAM card again today. Unfortunately, as predicted from the previous video, it has failed again. I'll give you a little demonstration of what the problem is. We just fill up an area of the RAM with zeros. Right. Oh, let's not go that far. That's better. Right. So you can see what's happening is that, remember, the RAM's actually interleaved. One bank, the bottom 4 bits are just reading back as all ones. The other bank it is perfectly okay, as are the top 4 bits on the right hand bank. I can just demonstrate if I do another fill. There you go, FF5. FF. Right, there we go. So again, we can see that the left hand bank is okay, the right hand bank isn't. Again, we've got just all ones in the bottom 4 bytes. Let me just switch the MDS off. Right, it's a bit quieter. Looking at the diagram, I'm pretty sure it's a data bus problem. What I've done a bit of prep work, and by pulling out some of the low byte RAM chips, I've determined that the bank of RAM chips that are attached here are the ones that are causing the problem. So I think what's happening is this buffer here is either not allowing data in, or the data coming out isn't correct. This is the other buffer, which is switched over by the swapping that we discussed in the previous video, which causes the interleave. You can see that these lines here are just joined back to the data bus here. So this buffer, I mean, they're the same chip, works perfectly, and this is the one I suspect the problem's in. Unfortunately, what we've got here is a live data bus, and it's highly likely that we've got things happening here as well, and here. So a scope or a logic probe, it's just not going to do the job in this particular case. So what I've decided to do, I'm going to hook it up to the logic analyzer, and I'm going to define this side as D bus for data bus, and this side as R bus for RAM bus. And we're also going to look at the chip select, which is on pin 1, and the direction, which is on pin 15, because this is a bidirectional buffer, of course. One other thing to note is, let me just bring the data sheet up. This is the one we're interested in, the 8226. Notice here that these buffers are actually inverting. you need to remember that, because otherwise the next part of the logic analyzer is going to be really confusing, because the data on both sides is going to be the complement of the other, i.e. it's inverted. So that's the plan of action. So what I'll do, I'll move the camera and then we'll have a look at the logic analyzer. Right, we're all set up, ready to go. The top trace is D bus, this is the data bus. R bus is the internal RAM bus, CS is chip select, and DIN is the direction line. What I'll do first is I'll just write some zeros and we'll see what happens. Right, so on the analyzer, hit turn. Right, there we go. Remember that the data bus is inverted, so we've got an F here. That's gone through the buffer and turned into a 0, which is what we'd expect. We can also see the chip select line going low here, and the data direction line is high. I'll do the reverse, that is I'll read that memory, then we'll see this line swap over. Let's do D8000, 9000, rearm. Right, there we go. You can see the data direction line is now low. Chip select's gone low as well. There's some jumping up and down here, that's just the data settling. But we can see that the RAM bus side is a 0, which is what we wrote in, and it's transferred back to an F on the data bus. Right, let's just try another figure. I'll put 5 in this time, and I'm writing a 5. So fill 8000, 9000, 05, rearm. Right, there we go. Again, an inverted 5, that's an A, and that's turning into a 5 on the RAM bus side. Again, we've got settling of the data here, but that's nothing to worry about. The data direction line's at 1 because we're doing a write. I'll do the reverse, that's doing a read, so I'll do display 8000, 9000, rearm, turn. Right, there we go. Data direction has changed state onto a 0, so we're actually reading out of the RAM now. We're getting 5 from the RAM bus side, and that's being inverted back to an A on the data bus side. So it looks like the setup of the analyzer is correct. So what we'll do now, we'll swap over to what I believe is the defective buffer, and then we'll see how we go from there. Right, I've connected up to what I believe to be the faulty buffer. First thing I'm going to do, I'm going to try filling the area with zeros. Let's arm the analyzer. Turn. Right, okay, so you can see immediately we've got a problem, because we should be seeing, because the data bus is inverted, this should be an F. You can see the chip select going low there. It was briefly an F before the chip select went down. We are getting the inversion, or whether that's actually true or not, I don't know, because it's inverting the 0 to an F. Let's try another number. I'll try putting 5 in there. Right, let's rearm, turn. Right, exactly the same effect. Absolutely no difference whatsoever. Again, we've got 0 on the data bus and F on the RAM bus. I'll do a read just to see what happens with that. Right, let's rearm. Right, okay, so this time we can see the chip select's gone down there. We had an F there for a little while, but of course the data's going in the other direction now because the data enable line's low, so it's read a 0 from the RAM bus side, and that's come out as an F on the data bus, which is fine. The problem with it is a little bit further along here. Looks like it's got an F on the RAM bus, and that's come out as a 0 again, which it would because it's inverted. But something's still not right, because as we saw on the previous shot, whatever we put into the data bus, it seems to be being squashed. I get a feeling that potentially what's happening is that the buffer is actually shorting the data bus on the bottom 4 bits. It may be something else, but I'm not really sure. I'm going to try changing that chip and see what happens. It's about the only thing I can do at this stage. In theory, that even if there's a problem on the RAM bus side, that shouldn't cause the data bus side to go to a 0. That seems really odd. So let's give that a go and see what happens. Right, I've replaced the bidirectional buffer. That's this one here. Did take 2 weeks to get it from Poland, mind you. That's the other side. Quite an interesting fault actually. I look at the logic analyzer traces again, and it's fairly clear that every time this buffer chip selected, it was actually clamping the lower 4 bits of the data bus to 0. And obviously we were reading that back as F because of the inversion on the data bus. So that's that one. It has cured the problem. I'll elucidate a bit more on that in a minute. If you are taking chips out of boards that are fairly old and sensitive like this, one little tip, just while I'm here, is to map out all the pins on the IC and where they go. Obviously you can do that from the schematic. There's a couple of reasons for that. Is that one, the schematics, back in when they were drawn, they were done by hand, and there was often a few errors on them. And two is that while you're extracting the IC, if you were to break any of the through plates or the tracks, if you don't know where they're going, you're going to have a really hard job putting them back again. The other thing you can see as well is that I've made an extra note here. When I removed the IC, there were several tracks underneath it. So again, you need to figure out where those tracks are going, because again, if they are broken, you need to fix them before you put the IC back in. Otherwise you'll end up links all over your board, which look a bit of a mess. So just something to remember. And once you've got the socket back in the board, or if you choose to solder the IC in, check again with a meter that all of the pins go to these positions you've mapped out, and that's going to save you a lot of time in the long run. Right, as I was saying earlier, this has cured the problem, no doubt. I ran the machine for about 4 hours. Unfortunately, just towards the end of that 4 hours, the whole block of memory on this board just vanished basically. I was just reading zeros back from it. Not a very complicated fault, luckily. This board, as I've said before, is usable in 16-bit systems, and this IC here is a 3 to 8 line decoder which decodes the pages of memory. I'll show you on the diagram in a minute, but basically we don't actually need this IC because we've only got an 8-bit system, but we do need one of the outputs to be low, otherwise the whole board won't be selected basically, and that's why I was getting zeros back and it was looking like everything was open circuit. So I've got this little link wire in here for the time being. I will have to replace this IC in time, so we'll put it back in the machine and we'll give it a little test. Right, this is the 3 to 8 line decoder I was talking about just now. You can see it's attached to the upper address lines. It's a bit confusing because Intel call address 15 ADF in hex. So AD10 I should say is the next address line up. These 10, 11, 12 and 13 go nowhere on our MDS-800 because it's only an 8-bit machine. They could potentially be used by a in-circuit emulator card, but not at this point in time. So basically all that happens is you can see these 3 resistors here. They're just pulling these 3 lines high. This one is pulled low through this link, and effectively that means this is selected, and output 7 on the 3 to 8 line decoder goes low, and that's then linked through to this little IC here, and that goes through and we get a 1 over here. So all I've done is my link goes from there over to there, I think, because I've got a link on E8, so that's what's going on. Right, so let's have a look at the actual MDS itself. I'll swap back to the terminal. Right, now we've got the operating system running, we can take a slightly different route into the monitor. So if I type debug, that will dump us in the monitor. We'll just assign the list device as we normally do. Okay, let's just do a substitute memory as we've done previously. So I'll do substitute B1000, 01, 02, 03, 04, 05, 06, 07. Just display that out. Right, there we go. So we're getting the right figures now. To get back to ISIS, we do an RST1. So if I do go 8, right, we're now back in ISIS. I can run my ported monitor now from disk. So if I type int m, that loads the monitor. What I'll do, as I did before, I'll switch off the internal monitor ROM so we can test all the memory. Right, okay, I think we're okay. So we'll do test 8000 to FFFF. Right, we'll just let it go around a few times. There we go. Obviously it's testing 32K in memory here, so it's going to take a little while. But that looks fine. So I think that'll do it for this video, and I shall see you next time.